Today's networks rely heavily on efficient data transfer. Ethernet LAN switching plays a crucial role in achieving this by intelligently directing network traffic. In this Blaxploit Network Pocket Tracer Home Labbing Edition video, I'm Damon Black, and we'll be diving into the world of Ethernet LAN switching using Pocket Tracer. A big shout out to Jeremy from Jeremy's IT Lab for creating this fantastic Pocket Tracer lab exercise. And to all of you viewers who want to follow along, be sure to download the Pocket Tracer file from the description below. Let's get started. Alright, let's take a look at our lab setup. We have a small network with two switches connected in the center. Each switch is connected to two PCs, forming a simple network topology. Crucially, both switches currently have empty MAC address tables, meaning they haven't learned the MAC addresses of any connected devices yet. Similarly, all the PCs have empty ARP tables, signifying they don't know the MAC addresses associated with other PCs' IP addresses. Now, the first step in the instructions asks us to analyze what messages will be sent over the network and which devices will receive them when PC1 pings PC3. This is a great opportunity to understand the communication process in a switched network. We'll need to consider ARP, which is Address Resolution Protocol, and how it helps devices discover each other's MAC addresses based on their IP addresses. Remember, switches operate at layer 2 of the OSI model, forwarding frames based on MAC addresses. Since the switches don't know the MAC addresses yet, they'll need to rely on ARP to learn them. Let's analyze this step in detail and then use Pocket Tracer simulation mode to verify our understanding. PC1, needing PC3's MAC address, broadcasts an ARP request through switch 1. Since switch 1 doesn't know the destination MAC, it forwards the entire ARP request out all connected ports except port F01. This is a network broadcast. Switch 2 receives the forwarded ARP request and, facing the same situation, broadcasts it further. Both PC3 and PC4 on the other end of the topology receive the request, but only PC3 recognizes its IP address 192.168.1.3 in the query. PC3 crafts an ARP reply containing its MAC address and PC1's IP obtained from the request, and unicasts it back to switch 2. This reply specifically targets PC1's MAC address. Switch 2 receives PC3's ARP reply, learning PC3's MAC address and efficiently forwarding the reply to PC1. PC1 receives the reply, discovers PC3's MAC address and stores it for future use. Now communication can begin. PC1 crafts a ping, ICMP echo request with its IP, sequence number, and the crucial addition PC3's MAC address. PC1's ping with PC3's MAC address reaches switch 1. Switch 1, remembering PC3's address from the ARP exchange, forwards it to switch 2. Switch 2, using its MAC address, directs the ping to port F01 connected to PC3. PC3 receives the ping, crafts a reply, ICMP echo reply, and sends it back with PC1's MAC address. Switch 2 and 1, using their MAC tables, efficiently forward the reply to PC1. PC1 receives the reply, signifying a successful ping to PC3. Alright, with our understanding of the ARP process, let's put theory into practice. On PC1, we'll initiate a ping towards PC3. Here we go. Now, to truly visualize the network traffic, let's switch to Pocket Tracer simulation mode. We should see an ARP request broadcast from PC1 targeting PC3's IP address. Both switch 1 and switch 2 will receive and forward the ARP request. Only PC3 will respond with an ARP reply containing its MAC address. The ARP reply will be unicast back to PC1. There it is. The ARP request is broadcasted from PC1. See how both switches forward it? Excellent. Only PC3 recognizes its IP address and responds with an ARP reply, and PC1 receives the reply learning PC3's MAC address. With this crucial information, PC1 can now send the actual ping data ICMP echo request directly to PC3's MAC address. Now moving on to step 3, since I had already sent a ping from PC1 to PC3, it's certain that switch 1 and switch 2 have learned these PC's MAC addresses, and so I'm only going to send a ping from PC2 to PC4 so as to generate some traffic and have the switches learn off their MAC addresses. Let's head on over to switch 1 CLI and enter privilege exec mode with command enable or EN and use the show MAC address table command to see which devices it has learned. This will display the MAC addresses of all connected PCs, PC1 and PC2, that switch 1 has learned through the ARP process. Now let's move to switch 2 and use the same show MAC address table command. This will reveal the MAC addresses of PCs connected to switch 2, PC3 and PC4 that it learned during the ping process. Whilst we're still in switch 2, we want to clear the dynamic MAC addresses it learned from the pings, which here is the final step of this lab exercise. To achieve this, we'll use the clear MAC address table dynamic command. This command will specifically remove only the dynamically learned entries from the table, not statically configured ones, if there were any, of which there was none. And by using the show MAC address table command, again we can verify that our cleanup was successful. Now let's switch over to switch 1. We want to perform the same cleanup here, similar to switch 2. Using the clear MAC address table dynamic command, this will clear the dynamic MAC address entries learned by switch 1 during the ping communication. And finally, we can verify the cleanup with command show MAC address table. And we've reached the end of the line of the Ethernet LAN switching. I know some of you might be feeling a little broadcasted after all that information overload. But hey, at least you're not as lost as I probably was while putting this video together. Yeah. If you somehow managed to understand everything, smash that like button. If you're still confused, don't worry, there's always a comment section below. Crush that subscribe button for more tech shenanigans, and hopefully next time I won't make any switch puns. See you later.